In this lecture, we're going to learn about continuous functions, at least be introduced to them. There's a lifetime of learning about continuous functions. We're going to talk about them in terms of being a basic stage of control. When you learned about these in Calculus 1, you may have been told that continuous functions were the ones that you could draw their graph without picking up their pencil. Well, that's not quite right. Let's get into the nuts and bolts of it. Let f from a to r be a continuous function where a is a subset of the real numbers, and suppose that a is an element of the set capital A. We say that f is continuous at a if for every epsilon greater than 0 there's a delta greater than 0, such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus f of a is less than epsilon. So this is to say we can control how far f of x and f of a are apart. We can make them closer by making x and a closer. Okay, now we say that a function f is continuous on the set A if it is continuous at every point in that set A. We're now going to prove a characterization of continuous functions in terms of how they relate to the limits of sequences. So again, our setup is suppose that f from a to r is a function on the set A contained in R, and that little a is an element of the set capital A. Then f is continuous at the point A if and only if for every sequence a sub n in capital A that converges to little a, the corresponding sequence f of a sub n converges to f of a. So a function is continuous if and only if it preserves convergent sequences. Okay. So this is an if and only if. So we will start with the supposition that f is continuous at the point a in the set A. And we'll prove that it preserves the convergence of sequences. So let the sequence a(n) be a sequence in capital A that converges to the point A. We will show that the sequence f of a(n) converges to the point f of a. Let epsilon greater than 0 be given. Since f is continuous at the point A, there's a delta, so that when x minus a is less than delta, then we will have that f of x minus f of a is less than epsilon. So by making x epsilon close to a, we will make f of x, delta close to a, we will make f of x epsilon close to f of a. Since the sequence a(n) converges to a, there is a number n, so that if n is bigger than capital N, then the distance from a(n) to a is less than delta. Now suppose that n is bigger than capital N, then the distance from a(n) to a is less than delta, and therefore the distance from f of a(n) to f of a is less than epsilon. And so from this we see that f of a(n) converges to f of a. Okay, let's now go the other direction. We now desire to prove that if whenever the sequence a(n) converges to a, it follows that the sequence f of a(n) converges to the point f of a, then f must be continuous. we will actually prove the contrapositive of this statement, which is if f is not continuous at A, then there is a sequence an that converges to A such that f of A, the sequence f of A does not convert, f of an does not converge to f of A. If f is not continuous at A, there is an epsilon greater than epsilon naught greater than 0, such that for any delta greater than 0, there is an x sub delta for which we have both the distance from x sub delta to A is less than delta, and the distance from f of delta to f of A is greater than epsilon sub 0. So it's not continuous anymore. So we if it's not continuous, we have to be able to have this condition holdings. Now, this is written in delta since we're interested in sequences. We want to switch off to having the natural numbers as an index. So for every n element of the natural numbers, choose an a sub n such that the distance from a sub n to A is less than 1 over n, but f of a sub n minus f of A is greater than epsilon sub 0. And so we can see here that the sequence a sub n converges to A by the squeeze principle, but f of a n does not converge to f of A because it's always at least epsilon naught far away. Now, this sort of theorem is called a characterization, this if and only if. It means we can swap freely between the condition of being a continuous function and the condition of preserving sequential limits. This is very, very useful in proving when a function is not continuous, and I'll try to work in some examples of that in future lectures. But it's also a tremendous addition to the theory. It enables us to prove some theorems without so much epsilonics. So this next one is an example. The following statements are true. If f and g are continuous at the point A, then f plus g is continuous at the point A. If f and g are continuous at A, then f times g is continuous at A. And finally, if f from A to R is continuous at A, and g from f of A to R is continuous at f of A, then g composition f is continuous at A. And these all will follow the same pattern, so I'm going to pick the most difficult one and prove it, and I leave 1 and 2 as exercises. Suppose that an converges to A, then because f is continuous at A, f of an converges to f of A. Therefore, since g is continuous at f of A, g of f of A sub n converges to g of f of A. That is to say, g of composition f of an as a sequence converges to g composition f of A, the point. It follows, therefore, that g composition f is continuous at A. And like I say, the other two are just as easy, but go through it yourself to see.